This is 3 mm, this is 2 mm, this is 6 mm. If you want to know at the middle what is the displacement, what we can do simply, if it is a linear element, we can take as average of, if you see all these things, 5 plus 3 8, 8 plus 2 10 plus 6 16. So at the middle it will become, displacement will be 8. Like that we could average it. That's how we interpolate the results if it is a linear element. So we do calculations only at the finite number of points, and then interpolate the results to the entire domain, so that entire surface we can come to know the results. So any continuous object has infinite number of degrees of freedom like this. It's just not possible to solve the problem in this format. So if we have so many number of points, it's not easy or practical to solve the problem, because there will be infinite number of joints.
Yeah.
So finite element method reduces the degrees of freedom from infinite to finite with the help of discretization. That's what I told. Discretization means like meshing nodes and elements. That's why we are doing meshing. We just want to discretize the discretize the element, so that we can make calculations only at a few nodes, and then interpolate those nodes to entire domain. That's how we can get somewhat realistic results and practically possible. Otherwise, if you go with like infinite number of joints, it's not possible to solve it. That's the main reason why do we carry out the meshing. So if we go to the next one, types of elements. What are the elements? If you see 1D element, 2D element, 3D element, and some special elements also there. If you see 1D element means you see this X, Y, Z. X direction dimension is much larger compared to Y and Z. This is X direction. So in this kind of situation we use these elements, we used to say that it's a 1D element. And if you see this one, the thickness of plate, it's very small. This direction and this like for example, this length is there as well as breadth is there, but the thickness is small. So we ignore the dimension y direction. Not ignore, we understand the wide one dimension is very less as compared to other two dimensions. So that's why it's called 2D, two dimensional element. And if you see 3D means almost all the directions, the elements are almost equal, approximately equal. We cannot ignore those dimension sizes. So we used to have 3D elements. So you see here, one of the dimension is very large in comparison to the rest of the two. Yeah, because one dimension is very large compared to the rest of the two. Here, two dimensions are very large in comparison to the third one. Here, all dimensions are comparable. So we cannot ignore any of them. So here element shape, we used to say it's a line element.
Yeah, because one
Here
dimension.
yeah, here line, here next one is quad element or tri element, we used to say. Once we go to the element types, we can understand like what even be quad and tri. And here this is the solid elements, tetra, penta, hex, pyramid. These kind of solid elements we have. If you are going to use the solid elements, different type of formulations, tetra, petra, hex, pyramid, all these things. And if you see here also, you see mass element. See, this is mass element. It's like a point element, concentrated mass at COG. If you have an entire top side, if you want to represent by mass, at the COG we can put entire mass just to simplify it. That's mass element. A spring, translational, rotational stiffness it has. Spring also we have translational spring, and rotational spring also we have. And if you see here, additional data from user, remaining two dimensions like a area of cross section that we used to give. Additional data from user is remaining dimension, that is thickness. And here additional data from user, none. We don't need to give anything. Once we define as a 2D element, we need to give thickness. Once we define the line element, beam element, we need to give the cross sectional area. Then only we can define it properly. So here element type rod, bar, beam, pipe, axisymmetric, cell, etc. Here element type is thin cell, plate, membrane, plane stress, plane strain, axisymmetric solid are there. And here 3 is a solid element. And here if you see damper also, it is the damping coefficient we used to define this one. Dynamic analysis, what we have seen, gap, distance, friction, all these things we can define as a special element. And practical applications, if we see long shaft, beams, pin joint, connection elements, etc. Practical application of the cell is sheet metal, plastic compounds like instrumental panel. Here the practical application is transmission casing, engine block, crankshaft, whatever like three kind of elements. All diamonds are comparable. Then we go for this 3D element. Okay. Is the rigid elements and weld elements and all we can use with this kind of special elements. If we go to how to decide element type. Element type, when we select, we are considering three kind of criteria. One is geometry, size, and shape. We saw that one dimension is whether comparable to other two or not. Like comparing the three dimensions, all three dimensions, that is the geometry, size, and shape. Another one is type of analysis. Which kind of analysis we are going to do, like linear analysis or non-linear analysis, or some thermal analysis or fatigue, crash analysis. Like the different based on the different type of analysis also we need to select the element type and time allotted for the project. This is also important. We cannot go with everywhere like a solid element. Somewhere we need to see the solution, how much time it is required for solving the problems also. Geometry, size, and shape. If you see, for analysis, software needs all the three dimensions. It cannot make calculations unless until geometry is defined completely. That is, we are missing there is nodes and elements, so we need to give all the three dimensions. Suppose if you are giving beam, we need to give the cross sectional area, and if you are giving the plate element, then we need to give the thickness. So all three dimensions will be giving it. If it in case of solid, automatically we are giving all three dimensions. So geometry could be characterized 1D, 2D, 3D based on the dominant dimensions and type of element is selected accordingly. This we have seen it already. If you see here, 1D element used for geometry is having one of the dimensions very large as compared in comparison to the rest of the two. So one of the dimensions is very large compared in comparison to the rest of the two. Rest of the two means other two dimensions. Here length is longer, like 1,000, but other two dimensions are just 5 and 10. It's comparably the x dimension is very large. And shape of 1D element is line. When the element is created by connecting two nodes, software comes to know about only one out of three dimensions. See, once you make two joints and make it line, one dimension it automatically comes to know what is the length. But whatever the other two dimensions we need to define. That's why the area of remaining two dimensions, that is area of cross section, must be defined by the user as an additional input data as into respective elements. Practical example, we have seen long rod, shaft, beam, column, spot welding, bolted joints, pin joints, bearing modeling. All these things we will see it later. And if you see 2D element used when the two dimensions are very large in comparison to the third one. If you see here, one dimension, x dimension is 500, z dimension is 300, y dimension is 2. So comparing to the third one, other two dimensions are large. That's why we are using 2D element. 2D meshing is carried out on mid surface of the part, here in the mid surface. 2D elements are planar, just like a paper of this page. By creating 2D element, software comes to know two out of the three required dimension. Once you make it 2D element, then it comes to know two out of three dimensions, required dimensions it comes to know. But the third dimension, there is a thickness has to be provided by the user as an additional input data. The next one, why 2D meshing is carried out on mid surface? There could be a question like why we are doing at the mid surface. Mathematically, element thickness specified by the user is assigned half on the element top and half on the bottom side. Once we give the thickness, what it takes, it's a half above and half below. Hence, in order to represent the geometry appropriately, it is necessary to extract the mid surface and then mesh on the mid surface. Once we give the thickness, it is taking half above, half below. So practical example, if you see all sheet metal parts, plastic components like instruments, panels, in general, 2D meshing is used for parts having width to thickness ratio more than 20. Suppose if width is width to thickness ratio, length anyway 1 meter is there, width is 200 mm means if thickness is say 10 mm, then we can go with 2D element. If width to thickness ratio is less than 20, we can go with the 3D element kind of thing. Limitations of mid-surface 2D meshing. 2D meshing will lead to higher approximation if used variable part thickness. Surfaces are not planar, have features like features on two sides, different features on two sides. Suppose if the thickness, say sometimes plate thickness we have like this also. So in that case also we need to define at the mid level only. That will give from here to here, it's a different thickness is varying. So which thickness you will use, we will use the minimum thickness kind of thing for our analysis conservatively. That's why it's saying that some higher approximation that's needed when we are going with variable part thickness. 3D elements, if you see when used when all three dimensions are comparable. So these three dimensions are comparable. That's why we are using for these three solid element, 3D elements. Transmission casing, clutch housing, engine block, connecting rod, crankshaft. These are the practical examples. Based on type of analysis. Structural and fatigue analysis use quad hex elements are preferred over trias, tetras, pentras. So you know like what are the fatigue analysis also we are going to do it. So in that kind of analysis we use quad and hex we prefer comparing to trias, tetras, pentas. Crash and nonlinear analysis priority to mesh flow lines, brick elements over tetrahedron. This tetrahedron brick, all these things we can see when we go for the type of elements whatever we are studying it. And mold flow analysis and all we are not doing it structural, it's mainly for mechanical. And dynamic analysis, when geometry is broader case as per above classification of a 2D 3D geometry, 2D cell elements are preferred over 3D. This is because cell elements being less stiffer captures more shapes accurately, that too with lesser number of nodes and elements. Cell elements being less stiffer captures more shapes accurately. So dynamic analysis, whenever you go, it's better to go with the cell elements because it's capturing all these modes accurately. And time allotted for project. If you see what it says, when time is no constraint, appropriate selection of elements, mesh flow lines, good mesh quality is recommended. Sometimes due to very tight deadline, analysis is forced to submit the report quickly. For such situations, automatic or batch meshing tools could be used instead of time consuming but structured good quality mesh. Just we wanted to know like quickly what is the approximate results and all, then we can use auto meshing instead of making it manual meshing and all. That's what it's telling. For 3D meshing, tetras are preferred over hexas. If assembly of several components is involved, then only critical parts are missed appropriately. Other parts either coarse missed or represented approximately via only elements bring. So what it means that whenever we study like some critical area, we can give more importance, more fine-tuned missing, but other areas we can approximately represent it. That should be okay. See, can we solve same problem using only 2D 3D elements? Can we solve? It's possible.
I think I will use 1D.
Yeah, you can use 1D. Is it not possible to use 3D elements for long slender beams 1D geometry and for sheet metal parts 2D geometry and 2D cell elements for representing big casing parts? The same geometry could be modeled using 1D, 2D, 3D elements. What matters is the number of elements and degrees of freedom, accuracy of results, and time consumed with the analysis. So you can represent it, but what matters is number of elements it will increase, a number of nodes and accuracy of results and time consumed also it varies. Okay. 1 minute, yeah. This person. For example, consider the cantilever beam, dimension 250, 25 mm, subjected to 35 Newton force. 1D beam model. See, 1D, we can make it like one node here, another node here, one line, and this length is 250. On cross sections 20 and 5, we can make it. And if you see one joint here, another joint here, right? So
Mhm.
here two nodes are there and only one element. So total degrees of freedom, if I see each
12.
node 6 degrees of freedom, here also 6 degrees of freedom, total 12 nodes only, 12 degrees of freedom only is there. And 2D cell element, same thing what we are
Wow.
making it, we are increasing number of nodes 900, element 800, total degrees of freedom you see 5454, because each node it will have 6 degrees of freedom. The same way in the 3D element, if you make it, number of nodes is this much and element is this much, and total degree of freedom is in solid 3D model, each joint will have only 3 degrees of freedom, not 6 degrees of freedom, because solids only have translational degrees of freedom, not rotational degrees of freedom. So that's why it's a 3, we are multiplying it, not by 6. Okay,
Mhm.
because nodes into 6, if you see here, node into 6, here also nodes into 6, but
Mhm.
here number of nodes into 3, because it's a solid element. Solid element, each node has 3 degrees of freedom. Okay, so
Mhm.
if you see the analysis wise, analytically, if you see our like theoretical formulas, if you see stress value is this much, displacement this much. If you use only element, node is this much, two nodes, one element, we are getting stress almost equal, displacement also equal. But in 2D element, node, how many nodes? It's increased so many nodes, elements also so many, but still it is not equivalent to theoretical value. Approximately it's equal. And if you go to 3D element, we have to go number of nodes too many, elements also too many, stress almost equal. So to get approximate result, we are increasing the number of elements. Number of elements, if increasing, means 52,000 equations it has to solve. Here only 5,000 equations. Here it's only 12 equations.
Mhm.
So that's why it's we can get the results, but it will take more time, and still it will take approximate result only. So we need to use correct element type. Okay, how to decide element length based on previous experience of similar type of problem, successful correlation with experimental results, and type of analysis, which analysis we are going to use, like a linear static analysis could be easily carried out to quite fast with high number of nodes and elements, but crash nonlinear CFD dynamic analysis consumes a lot of time. Keeping control of the number of nodes and elements is necessary. If these analysis and all we are doing it, and then we need to keep the number of elements, whatever necessary elements only we will keep, no need to increase the number of nodes. And hardware configuration also, graphic cards capability also, experienced engineer know limits of nodes that could be satisfactorily handled with the given configuration of hardware. Suppose you are part of a newly formed CA group, no clear guidelines are available, also there is no experience person in the group. In the first run, accept default element length, mess with the basic thumb rules as discussed in the book, run the analysis, observe the high stress region, remesh localized areas. Wherever we are seeing like some critical area, that area we need to remesh it. Otherwise, no need to do everywhere same mesh and solve again. Compare difference in original new results. Continue the process till the convergence is achieved. 5 to 10 percentage difference in strain energy or maximum stress value. So we can increase the number of elements and critical region, and we can compare with the previous result, current result, how much convergence is achieved, whether we are getting almost same result or within 5 to 10 percentage difference in maximum stress value, it should be okay. Like that, we can continue increase the number of elements. How to start meshing? Spend sufficient time in studying the geometry. Common observation is CA engineers start meshing immediately without properly studying the geometry and paying minute attention to the all requirements and instructions provided. Observing the geometry several times and thinking from all the directions is strongly suggested. So once we are given some work, then we have to see like whether it's a 1D element we can use or 2D element we can use. Like that we have to study it. If we are going with the beam members, then we can go with only 1D element. That's more than enough. Like that we need to study the geometry. Then only we can start go with the applying the meshing and all. And time estimation. Nowadays, trend is towards client or boss specifying time estimation for a given job, service price of it. Sometimes it is decided based on the mutual understanding. Time estimation is very relative and can find a lot of difference in estimation by different engineers. 3 times usually a less experienced person will estimate more time also. If someone is handling the job for the first time, then he will require more time. If kind of similar kind of jobs are given to same engineer again and again, missing time would reduce drastically. No, it's all like if you are doing the same work every time, then we will not take much time. If you are doing it something newly, then we will have different issues. So that's why it will take some more time. And if you see here, this is a geometry check. Once some CAD data is provided, whenever whatever software people might climb, but the ground reality is the geometry cleanup is integral part of the meshing activity. Before we do the meshing, we need to check some of the geometrical issues. These things and all we will see it once we make some answers, some small model. I think these things we will see it a little later. It's only the geometry only. If you see geometry check, complete part symmetry. 1 minute, huh?
Okay.
No. Yeah, yes, plus. Okay. Yeah, we are releasing it at equal angle. Equal angle we are doing it, but neoprene they told they can make it. No, neoprene they can manage it. That's what our Mohit is telling. Mohit, PMT. Yeah. Because miscellaneous one now we are not doing revising it only for one item, because when we go with miscellaneous revision, our structural item also there are so many things. Yes, correct. A role section only 4 items. So piping has given 2 item and the pipeline has given 2 item. Yeah. So yeah. Okay. Okay. Thank you. Mohit. Yeah. So here, if you see symmetry check, this member is there. Here we can. This is if we take this is symmetrical about this axis, and if we take this one, this is symmetrical about this axis. So this one small part only we can study. Once this stresses whatever it's coming here, it will be almost symmetrical. So we need to study like whether the part is a symmetry or not. If it is symmetry, we can study only the symmetrical portion. No need to study fully. That's why we, if it is a symmetrical structure and loading everything is same, then if I whatever the stress I'm getting here, it will be the same thing everywhere, because it's a purely symmetrical. Loading also symmetrical, as well as the geometry also symmetrical, means it will get the same results. Then no need to study the entire thing, no need to mesh it. Only one small portion we can mesh it. Meshing only quarter of the plate and reflecting it twice is advisable. Subpart symmetry repetition features possibility of copy paste comment. If you see this much portion, if you model it and we can take a repeated pattern, meshing highlighted 22.5 degree portion and then reflection rotation would lead to fast meshing as well as same structure of elements and nodes around the critical areas. Selection of type of elements. In real life, rarely we use only one type of element. It is usually combination of different type of elements, 1D, 2D, 3D, others. In the above figure, the handle of the bucket modeled by beam. This is the beam element, 1D element. Bucket body. Bucket body is a cell element. And connection between handle and bucket body through rigid elements. I think here. Yeah, that solid element will make it. Type of meshing. Geometry based. Mesh is associated to geometry. If geometry is modified, mesh will also get updated automatically. Boundary conditions could be applied on geometry like surface. FP based mesh is non-associative. Boundary conditions will be applied on the elements and nodes only. Join modeling, splitting the job, these things and all, it's okay. See one more thing here, if you see batch meshing or measurement, this is if you see here, more number of elements and more number of joints is there, the automatic meshing, but still not acceptable, because if you see this is the critical region. Critical region, we need to make this kind of fine-tuned model. So even though here number of elements more, but still we don't accept. Here number of nodes is less, elements also still, but this is professional level, it's okay. Because where the critical area is there, we have to make some fine tuning. Non-critical portion, no need to make very fine tuning. Even if we are having like a nominal mesh size, it should be okay. And meshing in critical areas. Circular areas are high stress locations. Dense meshing, structured mesh, no trias, PETAS is recommended in these regions. Areas away from critical or general areas. Geometry simplification course mesh in general areas recommended. That's okay. To reduce the total number of degrees of freedom and solution time. How could I know about the critical area before carrying out analysis? After going through the previous analysis report or similar part are carried out by your colleague or senior group, one can get fair idea about probable location of high stress. If you see here all these locations, there will be some high stress can happen. So this area we need to make it more fine-tuned members. General area we can make 4 to 6 elements. If you see here, this portion also it's curved portion, minimum 3 fill elements. Suppress small fill elements with 1 element for large fillets. Other areas, general areas. Critical area we can go with fine-tuned members. Right. Hello.
Yeah, I'm with you.
Yeah, fine, Mohit. Yeah, okay. Maybe after half an hour, now one small training is going on. Yeah, some presentation is going on. Yeah, yeah. Okay. Yeah, okay, okay. So if you see one of the dimensions is very large in comparison to the rest of the two. So we use 1D element, that is line element. Additional data what we are going to use is area of cross section, remaining 2 dimension. Element type rod, bar, beam, pipe, axisymmetric cell. Practical applications, I think this we have seen already. See types of element, 1D element, rod, bar, beam, pipe, axisymmetric. Rod is used for tension compression, torque also for some softwares. UY RY 1/4 tension compression member, shaft subject to torque connection elements. Here bar is all 6 degrees of freedoms are there. Here rod means it's only uh, axial kind of thing. Here it has all bending also. Applicable for symmetric cross sections. Shaft subject to multi-axial loading, bolted jointed connections. Same as bar, but also support unsymmetric sections, that is shear center and warpage. So bar and beam, there is a difference is that unsymmetric cross section. Unsymmetric cross section means sometimes this is one side symmetric, but other side it's not unsymmetric. So shear center, warpage, these also it is supported by beam element, but shear center warpage is not supported by the bar element. So pipe is same as beam except it has internal non-zero diameter. Axis symmetric cell, it is like a symmetric, for example circular is there, and means if one small portion, if you take this one, you can symmetrically you can rotate it, means like it will become complete tubular element. This is for same as bar for unsymmetric cross section. This is important. Same as bar plus unsymmetric cross section. Piping system structural analysis, thin cell pressure vessel cylindrical conical subjects. Okay, stiffness matrix derivation. What is stiffness? Why do we need it in FEA? Stiffness is nothing but force per length. Physical interpretation, stiffness is equal to force required to produce unit displacement. For example, if you take a cast iron, you apply some force from here to here, 1 mm. If you want to elongate it, how much force you are applying? Force divided by unit displacement. That's called stiffness. Force required to produce unit displacement. Stiffness depends on the geometry as well as material properties. If you see cast iron, mild steel, aluminium, if you apply the same force, all three will not give the same displacement.
Yeah.
Aluminium may give more displacement, mild steel may be less, because aluminium may be less stiff. That's why it depends on stiffness depends on the material property as well as cross-sectional property. That's why suppose axial stiffness means we will say PL by AE and all we will tell. It depends on the geometry as well as material property. But consider 3 rods of exactly same geometrical condition dimensions: cast iron, steel, aluminium. If you measure force required to produce 1 mm displacement, cast iron would require maximum force for by steel and aluminium, because Cast iron stiffness is more compared to mild steel and aluminium. Now consider three different cross-sectional rods of the same material. Again, force is required to produce unit deformation will be different because here it's a cross-sectional area is large. Here cross-section is less. Here it's a little less. So based on the cross-sectional area, also here more force is required to produce unit displacement. So stiffness depends on the geometry as well as material. Importance of stiffness matrix. You might have seen this. For structural analysis, stiffness is very important property. Equation of linear static analysis, F equal to K into D. We know what is the force equal to displacement, stiffness into displacement. Force is usually known. Displacement is unknown and stiffness is characteristic property of element. This means that if we formulate stiffness matrix for a given shape like a line or quadrilateral or tetrahedral or analysis of any geometry could be performed by measuring it and then solving the equation. Once we know the stiffness, then we know the force. We can easily calculate the displacement. So formulating this stiffness matrix for different types only, it's we have to do it. So methods for formulating stiffness matrix. There are three different methods: direct method, variation method, weighted residual method. And direct method is easy to understand but difficult to formulate. Computer programming, while weighted, variation weighted are difficult to understand, but they are easy for programming point of view. That's the reason why all software codes use either variation or weighted residual formulation. Raw element stiffness matrix derivation with direct method. If you see one example, maybe assume there are n degrees of freedom for a given element like quad 4 elements. Total degrees of freedom is 4 into 6 is 24. Assume first degrees of freedom is not equal to 0, rest are 0. This will lead to equation 1. Assume second degrees of freedom is not equal to 0, rest are 0. This will lead to equation 2. Like that, we will have n number of freedom. Then we will have the total stiffness matrix and almost like n by n we will be having it. If you see here, for example, there are two joints, right? So here force we are applying it. Case 1, u1, ui, this I joint is greater than 0, uj is 0. That means summation of force at x equal to 0 means f1 plus fj equal to 0. f1 equal to minus fj it will come. Axial stress equal to f by a. Strain equal to what is the displacement divided by overall length. So we know the stress is uh,
Stress
strain into
area.
young's modulus. So we know the FIA equal to U by L. So from this we will come to know what this is the stiffness value AE by L. So this is a stiffness matrix we can come to know from here. AE by L, AE by L like that it will come. So 1 minus 1 minus 1 1, this kind of equation it will come for the second node. And U1 U2 it's a 2 by 1 matrix. It's a stiffness matrix 2 by 2 matrix. So overall we will be having it a 2 by 2 matrix because it has only 1 and 2 joints we have taken here. 1 degree of freedom, this also another degree of freedom. So simple uniaxial rod we have taken. So stiffness matrix, if you see property in the diagonal term is the right, that is always positive only. Order of stiffness matrix corresponds to total degrees of freedom. So this order is corresponds to total degrees of freedom. Here now we have 2 degrees of freedom. That's why it's a 2 by 2. If it is 6 degrees of freedom, 6 degrees of freedom is 12 means here 12 by 12 stiffness matrix will come. Singular stiffness matrix means structure is unconstrained or rigid body motion is there. So whenever we come to know in the analysis, like it is saying that it is a rigid body motion or a singular stiffness matrix, software will give error singular stiffness matrix. That means entire thing is without any boundary condition. It is the structure is there. That's why it can make rigid body motion. Each column stiffness matrix is an equilibrium set of nodal forces required to produce unit respective degrees of freedom. Symmetric stiffness matrix shows force is directly proportional to the displacement. Diagonal terms of the matrix are always positive. That the force directed in say left direction cannot produce a displacement in right direction. Yeah, if you apply force in this direction, it cannot go negative way. Diagonal terms will be 0 or negative only if structure is unstable. Okay, these are the usually we study this in college. Raw elements support only tension compression and no shear force, no bending moment and torque. In the above equation, order of stiffness matrix 2 by 2, number of unknowns also 2. Number of unknowns is number of degrees of freedom minus number of degrees of freedom constrained by a single point constraints. Usually in comparison to the total degrees of freedom model, constraints are negligible. Hence, approximately the total number of equations equal to total number of degrees of freedom. Order of stiffness matrix equal to total number of degrees of freedom equal by total number of degrees of freedom. That's what 2 by 2 we have seen. So quad element, if you see here, we have 4 nodes. Degrees of freedom per node is 6. In each joint, 6 degrees of freedom are there. So 24. So order of stiffness matrix will be 24 by 24. Only for this element, 24 by 24 stiffness matrix will be there. That's the size of the stiffness matrix. This means we have to solve a single quad element. Software will have to solve set of 24 equations internally. Here, if you see tetra element, it has tetra 10. 10 means 10 joints are there. So each joint 3 degrees of freedom. So total 30. So order of stiffness matrix 30 by 30. For a given FE model, how many equations software solves? Assume there are 20,000 nodes means 6 cell model means 6 degrees of freedom per node. So it will take 1,20,000 equations it has to solve. Number of equations FEA will solve internally is 1 lakh, I mean 120,000
Wow,
equations. Yeah.
too much.
Table on equivalence of various lithium beta residual soil mechanics. Let us see here. See, there are 2 different methods also there. Rayleigh's Ritz method, Galerkian method, and all. Here we know that stiffness value and displacement also, like the equations for the bending formula and all is there, right? Dy by dx squared and all it will come. This all these partial differential equations it will come. Here Rayleigh's method and Galerkian method. These things are it's okay. This they will call natural coordinates in this Rayleigh's method. Here also Galerkian method like that they used to call, like here different shape functions and all they will be using it. Ni and it's a shape function. These things we will see it little later when we get to know on the next levels. And if you see finally ultimately what we can see that it will be both are used for the uh, stiffness matrix to derive the stiffness matrix only, and it will give the same results only. It will not give something different. If we let us see one small example, raw element subject to tensile force 100,000. So analytical solution means normally what we will say F by A, our
Yeah,
hand calculation. This is the stress. Displacement we know FL by AE, that 0.12 mm it will produce at this tip. If I pull it, it will come 0.12 mm. How to solve using software? So following steps are required in any commercial software. The sequence of steps input data may vary from software to software. Beam section, if you see define circular cross section, we need to define it. Then we need to, second step is mesh, we have to do it. First we have to create nodes. Nodes means in SACS also you are going to put joints. So first create joints and manually key in coordinates, coordinate of this joint and coordinate of this joint, and create a raw element by picking about two nodes. So after that we have to go to add a beam. From here to here we need to add member, and we need to assign that what is the member, assign cross sectional property, and create material and assign to the element. What material, like that we have to assign it. Then boundary conditions, we have to give the boundary conditions, specify type of analysis, linear analysis, we have to apply the force, and we have to give the restraint and solution. We can solve the solution, we will get the solution for each step. And post processing we can get the displacement, stress, we can animate the deflection, compare analytical versus software results. How software solve this problem internally? We know AE by L, that is the stiffness. 1 minus 1 minus 1 1, this is the stiffness matrix, this is the displacement, and we know that F1 is the, it was restrained, so that will become 0. Minus 10,000 plus 10,000 is nothing but the reaction. If you apply here 100,000, here automatically reaction will come. That's minus 10,000, 100,000, here 100,000. This all this value if you plug it, U1 is 0. We know the displacement, so we can say that U, if we solve this one, we will get this U1 is 0.12. Stress is 50.9. That's what we calculated here also. Like this we can solve it. A rod element cannot resist shear force. If a rod element is there, it cannot resist the shear force.
Everything is same as x1 except the force applied along y-axis. Instead of this way, we applied y-axis. Compare FA results with hand calculation. FA will show very large displacement, zero stress. This is because a rod element does not have a required degree of freedom to resist vertical force. That is to keep the system in equilibrium. If I apply the force here, it should be able to resist the rotation also. If a rod element means what will happen, it will rotate like this. It will not be able to resist this. Only beam element can resist because it does not have the degrees of freedom.
That's why we should not use element type rod for this problem. We have to use beam element. Okay, so what do you feel? Which degrees of freedom required to resist the vertical force? Rotation also as well as vertical also. To resist vertical force, we need an element which supports the translation along y-axis and rotation about z-axis. This is the z-axis. So it should be able to resist about z-axis rotation and translation also. It should not simply, it's not, when we apply force, it's not move like this. This is the force we are applying. It's not move like free fall. It's not happen. That's why we need to resist y direction as well as rotation also. So these of freedom are supported by beam and bar elements. If the same x is repeated with the beam or bar element, then one would get the correct results. In real practice, very rarely single element is used for analysis. It's a combination of many elements we have seen, right? Multiple elements we will be using it, not like only one element in real time. Stiffness matrix assembly of two rod elements. See here, one rod element is there, another rod element is there. This area is different, this area is different, length also different. Because the force is applied at point 3, what would be the force at points 1 and 2? I think here also same force only it will come. Before reading the answer, please this we will see in the book. Okay, for equilibrium equation, reaction at force point 1 is minus F at point 2, 2 equal to 0. Free body diagram, if you see it, F here minus F, the same F, and here minus F. At 2, if you see it, it will be the 0 only. Total force at point 2 is minus F plus F is equal to 0. In any finite element model, summation of forces and moment is 0 at internal loads, except the nodes at which the external force or moment is applied. So in between, this is internal load. In the internal load, if you add all the forces or moments, it will become 0. But if you see here, what is the force? Whatever the applied force, it will come. But if you see here at the fixed point, what is the force? The reaction will come. So any in between forces, it will be always 0 because to maintain the equilibrium. So overall summation of forces and moments for complete model will be 0. If we add completely, F minus F equals 0. That's why it's an equilibrium. This is one of the important checks for ensuring correctness of analytical analysis results. Assembly of elements. This is the first element. This is stiffness and the first joint, second joint, A by L. The second element 2B, 3. This is also stiffness value. If you see first element F1, F2, 2A, this one is not there. Here K1 minus K1 minus K1 plus K1 it will come. Third one is 0, 0. U1, U2A, 0. And second element, if you see first, if F1 is 0, F2B, F3, and 0, 0, 0 for first one. Second one is K2 minus K2 minus K2 plus K2, U2B, U. If you add all these things, you will get like this. K1, K2. But still it will be the positive value here. It will come. U2 plus UAB. Finally, you will get like this kind of a 3 by 3 matrix because we have 3 joints, right? 1, 2, 3 joint, 1 degrees of freedom like that. So assembly of two rod elements you have seen like L1, L2. If you make it, then we can get the equations. U2, how much is the displacement? U3, how much is the displacement? 0.1, 0.15. Like then we can see it. If it is a beam element is most general type of element. 6 degrees of freedom per node. And 3 translation, 3 rotations are used frequently for various applications. That's why each degrees of freedom here 2 node, each node 6 degrees of freedom. Total 3 translation, 3 rotation means 2 into here 1, 2, 3, 5, 4, 5, 6. Here also 6. So total 12. 12 by 12 matrix you will get like this 12 by 12 matrix. Fx, Fy, Fz, Mx, My, Mz. For second joint also Fx, Fy, Fz, Mx, My, Mz. This is the force. This is the stiffness. This is the displacement.
So beam bending, and this exercise same as exercise 2, except rod element replaced by beam element. Since the beam element has 6 degrees of freedom, means analytical software results will match properly. If I apply the load here, cross sectional here, see multi-axial loading, axial bending torsion. We can see this vertical plus axial plus rotational torsion also we can put it. Axial stress produces nominal stress. Bending it will produce stresses like this. Torsional it will produce like this kind of torsional stresses. This I think we have seen all these things, right?
Yeah.
At point A is nothing but this point. Maximum principal stress equal to sigma x by 2. This is sigma x by 2 square root of sigma x by 2 whole square plus tau square. This is a principal stress, CS stress, 1 my stress. This we will see it in the stress values when we can get it. Importance of boundary condition. This is important. If you see, like when we apply 30,000 with the 3 joints we have created, 3 nodes and 2 beam elements also created. Apply force at the central node. Central node we apply the force and appropriate boundary condition on one ends. Here and here we will give some boundary condition. Solve and compare the results. If applied boundary conditions are correct, then results would match with the following. 1 by 8 PL by 3 cube. This is for the displacement. Stress is PL by 4 M moment. This is also for the displacement 2 by 384 PL cube by 3A. This is the bending moment is PL by 8. If your answer matches the second set of formula, it means fixed boundary condition. So what does it mean? If you see here, if you are applying the force like this, it will rotate like this. Right? You can see the rotation here. If it is simply supported. If it is fixed, you cannot see the rotation. Rotation is 0. Then it will displace like this. Here displacement you see, and here also displacement you see. If you see simply supported, you see stress 76, displacement 0.64. Fixed, it's only half, and displacement 1 by 4th. So when we are giving the boundary condition is very important. If you are giving wrong boundary condition, it's a problem. That's why if you see here, difference between about two boundary conditions is just because 1 degree of freedom, that is rotation about z axis free in case of simply supported, and fixed for fixed. There is a drastic change in stress and displacement results. You see, stress differ by a factor of 2 and displacement differ and displacement a factor of 4. Now imagine a real life steel structure which is simply supported being modeled by C engineers fixed by mistake, and the analysis will show 200, and displacement also it will be very less. Since magnitude of stress is less than yield value, we will say that this is very easy and this is passing. Colorful impressive report with powerful presentation. Suburban animation files would be submitted to design engineer with the conclusion design is safe. But in real life, since that is simply supported, magnitude of stress will be double 400, displacement 4. That means the structure will fail soon. So it's very important to see the boundary condition. If it is simply supported, stress is different. Fixed stress is different. Almost two factor of different by a factor of 2. Displacement also different by a factor of 4. So boundary condition takes at least time only, but most important step in FEA. Typically brick meshing or something like a one cylinder engine we are making, it means it requires 300 hours and boundary condition just 8 hours. But 300 hours of hard work will go in vain if boundary conditions are not applied properly. You understand, right?
Yeah.
Yes, okay. Special features of beam elements. Sometimes when we model beam like this, we want to rotate, we can make some orientation of cross section, because I-beam sometimes we model like this or sometimes like this also columns, so the orientation it will be there. And taper elements also it is possible. And if you see beam shortening, beam end shortening, if you see here, the beam it goes until the middle, but actually it will come only in the face. So this kind of adjustment it will be there in the software, it's possible. And curved beams also we can make it. And offset means like this is original and this little bit above, see here you can see this offset to realistically represent the structure. We used to give sometimes offset also. Yes, and this is one important thing I wanted to say you. It is applicable only for non-symmetric cross-section. You see, this is non-symmetric cross-section, this is symmetric cross-section. This is not applicable for here, but it's applicable for here. Like angle, channel, and all, it is non-symmetric. When a vertical force, shear force is applied to the symmetric cross-section, if you are applying symmetric cross-section vertical force, it will bend only. But if you apply the same force here, see non-symmetric cross-section force, it will result in bending as well as twisting also. It will bend, at the same time it will twist also. So it will come like this. And the C section, it will twist as well as bend. But I section, it will bend only. And the twisting is due to unbalanced shear forces in the flange. You see here,
Yeah.
P1 here and P1 here.
Yeah.
So this is rotating it. But
Yeah.
here, if you see, this
Equilibrium.
P1 is cancelling, this P1,
Yeah.
this P1 also, it's cancelling what are the shear forces coming. So it goes like this, it goes like this. Here it comes like this.